Swayam Prabha. Digital India. Educated India.
This lecture is on photogrammetry. Today we will see basic concepts as well as the principles of photogrammetry and their application. So let us start with the definition of photogrammetry. So what do we mean exactly by this photogrammetry term? So photogrammetry is the science of obtaining reliable information, right, about the properties, and properties are like shape, size and position of any object or the surface from a remotely sensed image, right. So here basically we want to extract the information related to shape, size and position etc. of an object or the surface which is acquired by the remotely sensed image, right. The photogrammetry term is derived from three Greek words. First one is phos or phot, that meaning is light, gramma, that means to draw, metrin, that means to measure. So basically we want to draw, measure the shape, size and position and other properties of an object or the surface from a remotely sensed image, right. So that is the meaning of photogrammetry. Now there are different types of photogrammetry. So first one is aerial photogrammetry or space-bound photogrammetry, and the next one is your close range photogrammetry. So here you can see different acquisition mode for these different types of photogrammetry. So let us start with the first one. Here in case of aerial and space-bound photogrammetry, basically we rely on the sensors which are placed in space or in a aircraft, right, and there we are acquiring same area from two different positions, and that we use to identify the shape, size and other properties of the target. Here in close range photogrammetry, let us assume this is my target, right, and we have sensors with us. So first I will take from this position the image of this house, right. In the next one I will change the position from here to here, and then I will capture the same object, and again I can change, I can move and I can acquire the same target, but the view angle will be different. So tilting will be there for the photographs, but I can capture more information of target if I am changing the position, right. So this is how we are going to derive this properties of any object or the target from this photogrammetry. So let us understand what is the difference between aerial space-bound photogrammetry and close range photogrammetry, their strengths and weaknesses. So this aerial space-bound photogrammetry, this is used for the mapping of Earth and planets. This is well known. Image acquired through aircraft or spacecraft. So here the images which we will be using, that will be acquired by any aircraft or maybe from a spacecraft, right, and here the target will be ground surface, and the images are processed to derive new spatial information. So here basically we are talking about the satellite remote sensing, satellite images. In case of close range photogrammetry, we rely with our normal camera or handheld camera or the sensors available to use in the field. So here it is used mainly for industrial purposes, right, where you need more accuracy. And then the second one is imagery through handheld instruments. So this is very important. This is the major difference between space-bound and close-range photogrammetry. And then the target will be here. You can highlight any objects, not only ground surface, but you can highlight the object, or you can acquire, or you can study the objects, and you can also focus on a particular area, right. And here also, if you process these images, you can derive spatial information about that target very easily. So let us understand what are the different types of devices available in remote sensing. So if you see here, we have two different categories. First one is active system and next one is passive system. So I hope you remember these two terms. Active system means you have your own source of light when you are engaged in imaging. In case of passive system, we are using solar energy as source, right. And here if you subdivide this passive system, so here you have imaging system, framing system and non-imaging system. So in imaging system, basically we have push broom and whisk broom. This is known to you, right. Then in framing system, analog cameras are used and digital cameras are also used. But in case of non-imaging system, we have spectroradiometer, atmospheric profiler, altimeter. So what exactly we mean by this non-imaging system, that I will explain you. So let us understand the sensors which are launched in the space, they are also capable of working on the ground, right. So in certain environment. So when we have the same instrument for ground measurement, then what we do, we take them to the field and then we have a fiber optic cable through which it can sense the energy, right. So let me redraw this figure and then you will understand it. So in case of space-borne satellites, we have many detectors attached here, right, and simultaneously they can see our ground surfaces, and the resultant imagery will have pixels, right. So we can easily generate the image. So this is the imaging system. But in case of non-imaging system, part of this sensor has been designed to use in the ground. So what happens here, you have a sensor and here you can see only one particular area at a time. So what will be the output? You will have values, right. So if we are talking about this spectroradiometer, so then we can have two columns. One will be your wavelength and another will be your reflectance. So in wavelength, it is based on the specification of this particular instrument, spectroradiometer, whether it is designed to capture 100 data in 10 nanometer interval or 20 nanometer interval or 1 nanometer interval. Depending on that, it can measure the reflectance value for the given object. So here if you see the based on the field of view, right, this is the field of view and this is the coverage on the ground. So depending upon the height, it will cover your target. So you have to make sure it is seeing your target when you are engaged in acquisition. So in this case, you can acquire the response of your target in several wavelengths, but that will be only for one particular area. So this is called non-imaging system, right. Here the output will not be in terms of image. Here you can generate the spectral profile of your target. Similarly, atmospheric profiler, this is used to see or study the atmospheric constituents using this wavelengths. In altimeter also the same principle works. So, here also we can measure the points, right, the response of your object in terms of elevation, in terms of atmospheric constituents, in terms of reflectance, in terms of emissivity, in terms of transmittance. So, it depends on your application and the instrument you are using. You can have several measurements. So, let us understand what are the different advantages and disadvantages of aerial photogrammetry. So, first advantage of aerial photogrammetry is stereoscopic imagery. So, what we mean by stereoscopic imagery? That for the same ground, suppose this is the target, then in the first acquisition you have covered maybe this much area, like half of your study area. So, this is the first scene. Now, in the next scene it should have overlap, right. So, for the overlap reason you will have extra information captured from different position, right. Then you will have third image and here you will have this rest of the area. So, you can see this area has been captured by first, second and third image. So, like that if you have the overlap images, then they are known as stereoscopic imagery, right. Now, the next advantage is it can provide flexibility in image acquisition time, right. Then the third one is higher spatial resolution. Since aerial photogrammetry can be done using this drones or maybe helicopters or maybe aeroplanes. So, obviously your altitude will be lesser than the spaceborne satellite. So, in that case what will happen? The FOV is there and based on this height the coverage will be much smaller. So, when you have a smaller coverage area, then the pixel resolution or the spatial resolution will be very high, and it is a well established technology. Next point is it gives control over the whole acquisition process. So, here basically what I mean, you will have the full control of this image acquisition in terms of timing, whether you want to do it in the morning or in the afternoon or maybe in the evening or maybe in the night, depending upon in which wavelength you are working and what is your application, right. So, like that you will have many other flexibilities when you are going for aerial survey or aerial photogrammetry, right. Next is disadvantages. In disadvantages, it is very expensive because you have to hire drone or maybe you have to buy a drone, you have to hire a helicopter or aeroplane, then sensors you have to buy. So, everything will become very costly. In the next point, it is very difficult to cover the same geographic area in same scene. Why? Because suppose if this is your study area, this was the first acquisition. In the next acquisition, basically what you did, you changed the position and from here you have captured. So, you have to maintain the position so that in the first it has acquired this, second I want to acquire this only, right, not like from here. So, you require very high precision here. So, it will be very difficult, it is not a very easy task. So, that is why it is difficult to cover the same geographic area in the same scene. And one more thing, you may want to capture this particular area in your first scene, but depending upon the altitude and the FOV you are using, maybe the first scene may cover only this much area, right. So, this particular object can be captured in two images, not in one. So, that is again the another limitation of this aerial photogrammetry. and illumination condition changes with time because sun is moving. If you are engaged in passive remote sensing, illumination condition always changes with time based on the sun's position. So you have to correct for the illumination errors. Now the next is, it is very important to note that for aerial image acquisition or survey, government permission is essential. You cannot go directly and fly your craft and you can capture this. So you need to have proper permission for this. Now let us understand what are the different geometries involved in aerial photographs. Assuming this is my study area and this is my aerial survey vehicle, and here if you captured in this mode where you can see the sky or part of a sky along with your features, right, they are known as high oblique photographs, right. In low oblique photographs you cannot see sky. This is the basic difference between high oblique and low oblique photographs. So in high oblique you will have some portion of sky, whereas in low oblique you will not capture any of the sky, you will have only ground. In case of vertical photograph, you are actually following the nadir, right. So nadir will be the center of your photograph. So if you do that, then only the rooftop of this particular house will be visible in your vertical photograph. Whereas in low oblique photograph and high oblique photograph, you can see the base as well as sides of the objects. So this is the basic difference between vertical, low oblique, high oblique photographs, right. Let us understand in detail these vertical and oblique photographs. So here in vertical photos, basically it is nadir looking. This is very important. Then in tilted photograph, and which is basically 1 to 3 degree of nadir, that is the minimum requirement, then only it qualifies for this tilted photographs, right. And in tilted photograph you have two category, first one is high oblique and second one is low oblique, and here this is the major difference. So it includes horizon. So in low oblique photograph, horizons are not included, whereas in high oblique horizons are included. So you can see here, this is basically the vertical photograph. But how do we say this is a vertical photograph? Because we have checked the nadir position. So if you see the nadir lies on the center of this photograph, then only this will qualify for this vertical photograph, right. Let us see one by one how these vertical photographs or nadir looking photographs give you the output. So assuming this is my target and this is my aircraft, and through which I am going to capture this house. So let us assume this is the nadir looking image. So in the nadir looking image you will see the rooftop of the objects, right, or the buildings which are in the center of the image, whereas as you go away from the center you can see some of the sides of the objects, right. So here you can see this is approximately nadir position of this photograph, right. But if you see the tilted photographs, low oblique photographs, you can easily see the sides. So this can give you some perception about the height. If you see the next category, that is the high oblique aerial photograph. So here you can easily find sky. So horizons are included in high oblique aerial photographs. So you can try this your own. If you take your normal camera or maybe mobile phone, you just pinpoint your target on the table, and from that you maintain the 90 degree and capture that. You can see only the top, right. But as you tilt your camera, you can see more objects and slowly if you tilt more, you can see the horizons in the outdoor, right? There is a concept called overlapping stereophotography. I have discussed this before also, but I want to explain in detail what exactly we mean by overlapping stereophotography. So let us assume again this is my study area and I have a aircraft through which I have started capturing this area. So first image will have this. So first image will be something like this, output of this first sensing. Then when we move our aircraft, then it will capture from here to here, right? Then again we are moving, then it will capture from here to here, right? Then we are capturing from here to here, then we are capturing from here to here. So you can see there is always a overlap, right? So these overlaps will help you in your study, that you will understand slowly, but basically here we are moving in this direction, right? And always we have some overlap in the next image, right? So it will appear something like this. So you will have all the images with some overlap, and then you can call it overlapping stereo photographs. So why we need this overlapping stereo photograph? This is required for this 3D viewing. So if you want to generate a 3D map of an area or of an object, then we need to capture all the sides including top, then only you can generate the 3D images. Or it can also help you to study the parallax. And what do you mean by parallax? That we will see. This is the same example I have put here. So here you are having all the images captured like this, and then it has moved and it is going like this, your aircraft. So here in this particular photography, we have maintained end lap 60%. So all the next images will have 60% image which is captured in the previous one. And once you move to cover this whole area, then the sides also, they should have some overlap. So it is something like this when you are capturing this one, right? So this overlap is basically 60%, and which is known as end lap. And when you are moving and again you will capture the next portion of this area, then this particular portion will be overlap. So this should be 20%, and they are known as side lap, right? So this is the difference between side lap and end lap. And when you are going for a overlapping stereo photography, then you should maintain at least this 60% and 20%, then only you will be able to generate this 3D, or you can study the parallax, and parallax will be used further in estimation of height of any object captured in that particular scene, right? So here you can see this is another example where this particular repetition in the first and second scene is 60%, right? So let us understand what is the difference between vertical and oblique aerial photographs and what we can do with vertical and oblique photographs. So in vertical aerial photographs, tilt angle is possible only up to 3 degree from nadir. So in vertical photograph up to 3 degree is allowed. In vertical aerial photograph, the scale is approximately uniform throughout the photograph. Why? Because you are going to measure this area from the top, and this is basically 90 degree, right? So if you see, this is your center of the image. So you will see the top of your building here, but as you go away, there will be slight change in the position. So you can see little bit of the sides of the corner buildings, right? So but assuming that this is very less or negligible, and if it is up to 3 degree only, then we say that this is a vertical aerial photograph. A vertical aerial photograph can be used as map because you are seeing from the top and there is no distortion involved in this vertical aerial photograph. Compared to oblique aerial photograph, vertical aerial photographs are easier to interpret because you know what is the spatial resolution, what is the distortion, what was the position of aircraft or spacecraft, and what are the different objects you are going to study. So it will be relatively easier and better input for 3D map generation. And once you know more information about your object or your image, the correction will be easier and it gives you better 3D output, right? But when you go for this oblique aerial photographs, your advantages are different and there will be certain disadvantages, but you have to decide basically what kind of photography you want to do. So compared to vertical aerial photograph, oblique photograph can cover much larger area in a single photograph. This is the main advantage, right? Then object height perceptions are very poor. So here when you are tilting your camera, you cannot say directly like this is the height of this building, right? Because everything is proportionally changed and there will be some error introduced by your tilting and the sensor. So object height perceptions will be very poor. Additional objects can also be visible in oblique aerial photographs because you are going to cover more area, right? So as I told you that this photogrammetry is to derive the properties of your object or the ground using this stereo pairs, right, or the aerial photographs, right. So here basically we want to identify or we want to estimate the scale. If you know the scale, everything will be easy, right. So let us understand what are the different types of scale you can use and what are the different application you have when there are certain known factors or known variables or known values are with you, right. So let us start by what do you understand by scale, and that too photograph scale, because now we are talking about the photograph. So here this is the ratio of distances between corresponding point on photograph, which is basically map, and on the ground, right. So this is the ratio, and in other words, scale defines the relationship between a linear distance on a vertical photograph and the corresponding actual distance on the ground, right. I hope this is very clear. This is very simple statement, so you can understand easily. Now let us see some example like scale. You might have come across this particular values. Like scale, people write 1:25,000 or 1/25,000. So what does it mean? It indicates like 1 unit on the image is basically 25,000 unit on the ground. Unit is, it depends, like if you are using meters, centimeter, inches, so it is up to the photograph or the area and what scale you are using, right. So it means that a length of 1 unit of measurement on the photo represents 25,000 units of measurement on the ground. So if we are talking about the satellite images or aerial images, we know the pixel size, you know the spatial resolution, so you can easily say that this is the size of 1 pixel, and 1 pixel or maybe one object which is on the ground maybe 1 meter, but in image it is coming 1 inches. So 1 inch on the image is equal to 1 meter on the ground. So that will be your scale, and that you can represent as 1:2, 250,000, 25,000, 1:1, 1:2, 1:3. So you can use whatever values you get from your image. So let us see there are few terms which you need to understand. First one is representative fraction, RF, right. So, now onwards I will call it RF. So, that is for the photographs. Then photo scale reciprocal, that is also for a photograph, and equivalence map, right. So, that is for the map. Now, let us see one by one what they exactly mean and how do we calculate them. So, first one is representative fractions or photo scale, both are same, right. The ratio of the distance on a photograph to the same distance on the ground, that is known as RF, and here you can simply take the photo distance and ground distance. Again, this is your image and there is a house, right. So, on image you know what is the distance between this to this wall, right, if you have a high resolution data. Then let us assume this is coming maybe 5 pixel. So, 5 pixel, that means 5 pixel into spatial resolution, right. So, if that is 5 into 2.5 centimeter spatial resolution, so that will be your distance on the image, and in the ground you can easily measure this. So, maybe let us say this is maybe 30 meter, right. So, this is 30 meter. Now, this value represents 30 meter on the ground. So, here photo distance will come and here ground distance will come. Like that you can easily calculate the RF, right. For example, if the distance on a vertical photograph is 1 and the corresponding actual distance on the ground is 14,899, then the RF will be 1 by 14,899. The both values are having same unit, so RF will be unitless. When you don't have the information about that object, that what is the size or what is the distance of that on the ground, then how you can calculate this RF? For that we use this formula, that focal length divided by flying height. So, this will give you again the RF, right. So, for calculation of RF, either you should have the photo distance or the ground distance, focal length, flying height, then you can calculate the RF value, right. The next scale is photo scale reciprocal, that is known as PSR, or photo scale factor, that is PSF, right. So, this is basically the ratio of the ground distance divided by the photograph distance, right. So, PSR is ground distance by photo distance. And for example, if PSR is 14,899, that means ground distance is 14,899 times of the photo distance. So, this is basically the inverse of RF, and this is again unitless. The smaller the PSR, the closer the photograph to the actual area. So, if the PSR is very less, then that means photograph and the real object, they are having similar dimension, right. Similarly, PSR can be calculated using this focal length and flying height using this formula, right. Now, let us understand equivalence. So, ratio of the distance on a photograph to the same distance on the ground and expressed as a ratio. So, here basically ratio of the distance on a photograph to the same distance on the ground and expressed as a ratio, right. So, for example, 6 inches is equal to 1 meter or 9 centimeter is equal to 1 kilometer, and usually these units are not same in equivalence, right. So, you have seen the scale, different scales we use in photogrammetry, but what is their variation, how they vary with respect to ground, right. So, apart from this scale, there is very important to understand this variation, right, because scale we identify for a particular object or for a particular scene, but on ground we have this elevation difference. So do this scale is consistent throughout the scene or they can vary place to place. So that you need to understand. So in a vertical aerial photograph, variation in RF will be negligible, right? Because in vertical aerial photograph, we assume distortion is very less and we are seeing from the top. So we assume this RF variation is negligible. So you can use this focal length and flying height above the terrain, right? Whereas in oblique aerial photograph, RF will be changed across the photograph because you have tilted the camera and then you have acquired the target. So here if you see, even in the vertical photograph, you can see the effect of topography, right? Since this is snow, you cannot see this. So here if you calculate scale here, if you calculate the scale here, if you calculate scale here, if you calculate scale here, that will be different. Why? Because you have to take care of the topography, right? So in that case, you need to calculate scales at different places even in a single image. So spatial resolution is a function of IFOV, view angle and topography. So this gives you a hint like how it can help you to estimate the scale, because every time you are going to calculate the photo distance, so it depends what was the elevation of the ground at that particular position and what is the spatial resolution acquired by your sensor at that particular location, because that is going to change the scale, right? Because as you see the topography effect on the spatial resolution, it is basically IFOV and this elevation. So it is very important to understand what is the effect of spatial resolution and IFOV and topography and then elevation, right? So this is one example I have put to understand what is the effect of focal length on the acquired image. So if you see here, we have, this is the focal plane, this is the lens, right, and this is the area which we want to capture. So here you can see this is different and this is different, right? So if you see the coverage of this particular setup or this particular instrument is basically less, but whereas if you see, this is the coverage for the same area when we have changed the FOV, and this is the effect when we have changed the focal length, right? So angle of coverage increases as the focal length decreases. So I hope you must have understood this. Now let us see some examples. So this is one question for you that you can answer, you can try, and the answer is already given in the next slide. But before going to next slide, you please try this one yourself and then see the answer, right? So here the question is, what will be the effect on PSR for flat terrain if the focal length is increased by 2 times, right? So here we know PSR is equal to flying height above terrain divided by focal length, right? And keeping the numerator flying height above terrain constant, PSR is directly proportional to 1 by focal length. So if focal length is increased by 2 times, PSR will be reduced to half, right? So therefore there will be change in the PSR with this, right? Now the next question is, find out what will be the photo scale reciprocal and representative fraction, that is RF, using the equivalence value, right? And equivalence is 1 inch is equal to 1 mile. So here this is the solution, you can go through it, you can calculate it, because this is very simple. You just have to correlate your basic understanding with the problem, right? So you have seen the different scale and you have also seen what is the effect of height, topography and change in the focal length on the image and how do we analyze them. So, let us understand different types of scale which are available. So, average scale is for the whole image, right, because sometimes you have to report what is the average scale or scale of this photograph, but sometimes you have to use nominal scale, sometimes you have to use point scale. When your surface is very undulating, you cannot use this average scale here, that will be wrong. So, in that case it is better to go for the point scale, right. So, in point scale, every point at different elevation will have different scale. That advantage you will have when you are using this point scale, right. So, for a vertical photograph, I have taken this A and B location and their distance, right. So, you can easily measure the distance between these 2 points on the photograph based on the spatial resolution, and assuming we have the ground distance, we have visited that particular place and you have calculated the distance between these two, or you have measured that, right. So, here we have few knowns like what is the photo distance, what is the ground distance, then ground elevation, and here basically this is the hint, right. So, here what you have to calculate? You have to calculate representative fraction, then photo scale reciprocal and then equivalence. How do you calculate? Using these formulas, right. Now, let us see, we have all these knowns, right, and for representative fraction for RF, you can use this formula and the values will be like this, right. For photo scale reciprocal, this is the value, right. So, all these problems you can try yourself before seeing the answer and then you match your answer whether it is correct or not, then you will learn more. In this particular case, I have kept this A and B here and they are separated with some distance, right, and here we have flying height above MSL, that is 8000 feet, elevation of area above MSL, that is 800 feet, focal length of lens, that is 6 inches, and here you have to calculate RF, PSR and EQ, right, and you just see the next slide after you are done with the calculation, right. So, here you can calculate RF using this formula, this will be the value, and for PSR this will be the value, right. So, you just calculate and check your answers. Here this is another example where AB are separated with these lines, and here you have map scale, map distance, photo distance, elevation of point A, that is 300 feet, and elevation of point B, that is 400 feet. Now, how do you calculate ground distance, right? Photo scale reciprocal, that is PSR, right? So, you can calculate using this, and PSR you can calculate using this. This is another problem where you have to estimate the flying height of the aircraft using following information. So, here you have photo scale reciprocal, average elevation of the ground surface and then focal length, right. So, how do you calculate the flying height? Now, this is the reverse problem. Now, you can always use the same equation by changing it, and then you can calculate what is the flying height of your craft, right. So, when remote sensing started, we started with the normal camera. If you find old vertical aerial photographs, you will find there are several marks printed on the photographs. This I am talking with respect to printed aerial photographs, right. And here this we are talking about fiducial mark. So optically projected geometric figures located either at the four corners or on the four sides of the photograph, right, and they are known as fiducial marks. They define the coordinate axis and geometric centers of any individual aerial photographs. In general, x-axis defines the direction of the flight. The intersection of the fiducial mark represents the principal point of the photograph, right. So that is the center of your image by joining these fiducial mark, right. So if you join them, these are fiducial marks. Now if you join them, you will find your principal point lying somewhere in the center of the image, right, and in general this defines the direction of the flight, which is mentioned here, and this has been captured like this. If you see, this is your lens, this is the principal point, these are the fiducial marks. So sometimes you may find this kind of shape, sometimes you will find some cross, sometimes it will be like this, right. If you see this photograph, these are basically fiducial marks, right, and it is very easy to locate on the image, and if you join them, you will find the principal point. Here this is another example, these are again fiducial marks, right. This is another example, this is another example, and when we join them, we find principal point, right. So it is very important to note that when you are joining the opposite corner fiducial mark and the center where they are crossing each other, that point is known as principal point. So in image, basically it will look like this, right. So principal point is the geometric center of the photograph and the intersection of x, y axis or fiducial marks, right. So it is very important that you should able to identify principal point PP in your photograph. Lens distortion is radial from the principal point. So lens distortion will be minimum at principal point, right. So as you go away, your lens distortion will be more. So let us see whether this principal point and nadir, whether they are same or different. So in a oblique photograph, your principal point will be somewhere else, right. In a vertical photograph, your principal point will be somewhere else, right, for the same area. So it is definitely the different points on your image. So nadir is the point vertically beneath the camera during the acquisition of photographs, right. And here if you see, this is the nadir point. So they are definitely different from each other, right. And topographic displacement is radial from the nadir. So topographic displacement will be very less at nadir. As you go away of nadir, you will find more topographic displacement, right. And there is a new term called isocenter here. So you have already seen this principal point and nadir, right. Now we have another point which is called isocenter. So isocenter is the point that falls on a line halfway between the principal point and the nadir, right. So where? Here. So this is your isocenter. The tilt displacement radiates from the isocenter. So now the tilt displacement will be minimum at isocenter, but as you go away, you will find more tilt displacement. So I hope you have understood the principal point. Now here basically we find principal point for two different images and they are basically stereo pairs. So stereo pairs are like 60% overlap will be there. So in the first image you see this particular feature is coming here, but in the next photograph it is coming here, right. In the previous photograph this feature was here, in the next photograph it is coming somewhere else, right? So what we will do, we will start marking the principal point on the first image. So here if you are marking this as a principal point by joining the fiducial marks, then in the next image also you will find this principal point. Now where this principal point is coming in the next image, that you need to find. So suppose we have marked here, so this will be here, right? So here this point will become conjugate principal point, right? So in a stereo pair, identified principal point of a photograph can be located in another image, right? This point is known as conjugate principal point. I hope this is very clear to you. So flight line can be determined by plotting the principal point and conjugate principal point in a line. So if you plot this, then this is the direction of flight. The shift in position of a landscape feature on a photograph that alters the perspective characteristic of the image. So film and print shrinkage, that is negligible. Atmospheric refraction of light rays, right, that is also negligible. Motion of the landscape feature, that also we consider it is negligible because we are maintaining that speed, right. Now the next is lens distortion. So lens distortion we cannot ignore. So how they appear in the image? So you can see this particular area, right. So you will find this curve effect. That is one example of this lens distortion. So here if you want to do some kind of a study, or if you want to find out the pixel size, they are different across this image, right. So you cannot really use this lens distortion image, right. So let us understand in terms of principal point, isocenter, nadir, how this lens distortion occur, right. So this lens distortion radiates from principal point, that you are familiar with this PP, right, and it causes landscape feature to appear either further away or closer to the principal point. Edges of the photograph are significantly affected, you remember last slide, and distortion curve developed by calibration of the lenses is used to avoid this particular error. Then the displacement is the shift in the position of a landscape feature that does not alter the perspective characteristic of the image. So here again curvature of the earth is negligible, tilt and topographic relief. So tilt displacement, it radiates from the isocenter of a photograph. So here this is the isocenter. It is caused by the aircraft not being perfectly horizontal at the time of exposure of the film, right. If the amount of tilt is known, photographs can be rectified. If we can determine the direction of the tilt in terms of upper side of the tilt and the lower side of the tilt, we can determine how landscape features are being displaced. The topographic displacement, they radiates from the nadir of the photograph. So here we have nadir, varies directly with the height of the landscape features and varies directly with the radial distance from nadir to the top of the landscape feature. There will be no displacement at nadir because you are looking just above that. Varies inversely with the flying height, and when you have this, you can always generate 3D images. So now let us start with parallax. So what do we mean by stereoscopic parallax? So here the most important step is to determine the orientation of photograph, right. In general, labels and annotations are placed towards the northern edge of the photograph. So if you see, this is the northern edge of this photograph. To confirm the orientation, map can be used for reference. You can use some previous images or the maps to reorient this if by mistake this has been wrongly put, right. So here what exactly we are doing? we are going to do the overlapped aerial photography. So adjacent overlapping aerial photographs are called stereo pairs and are required to determine the parallax and 3D viewing, right. So here this is the ground, and here for the first position I have captured this particular area. Now I have changed the position and then I have captured with some overlap, and then we can have the stereo pairs. Now for 3D viewing, stereo pairs are required with approximately 60% end lap and 20 to 30% side lap. If you have this, then only you can generate the 3D image of that particular area. Now for stereoscopic parallax calculation, what we have to do? First we have to identify the principal point, conjugate principal point, right? And then we have to find out the flight direction, and then we can calculate the stereoscopic parallax. So let us go step by step what we have to do. So stereo pairs must be oriented correctly. Then locate the fiducial mark, principal point and nadir in each photograph, right. Locate the conjugate principal point and principal point in both the images. Draw the flight line by joining the lines between PP and CPP. So PP is your principal point, CPP is your conjugate principal point. Align the photographs accordingly so that all the 4 points lies on the straight line. If you have this, then if you have a stereoscope, you can easily see the 3D of that area using these stereo pairs, right. So the displacement of an object caused by a change in the position of observation is called parallax, right. When we are seeing from here, we will see some feature of this particular object, but when we see from here, we will see another side or next information about the same target. And if we are changing the position, and when we have displacement of an object caused by a change in the position of observation is called parallax. Stereoscopic parallax is caused by taking photographs of the same object but from different point of observation. So if this is the line of flight, if you see this is one object and how they appear when you are changing the location, right, location of the observation. So they will appear differently. And here in this image you can see only top. Here you can see this side, and in this image you can see this side, right. So if you have this complete observation, assuming from here, here and here, you can fully cover this area, right, and you can estimate the distance between these top and distance between bottom. So here in this case you can see this bottom, so you can easily pinpoint it and you can take this distance, but here in this case top and bottom both will be same, whereas in this one also top will be different, bottom will be different. So if you are having such information, you can always calculate top and bottom distance from a stereo pairs. Note the displacement between top and base of the storage tower in this photo stereo pairs. Now here we have PP, CPP, and this is another CPP and PP, right. Once you have that, then you can easily calculate the absolute stereoscopic parallax, which is the average photo base length, right, which is average distance between PP and CPP. Here this is another example where this base distance is different, top distance is different, because in both the images none of them were vertical photographs, right. When you have such images with you, you can always calculate the distance between these two, right, and you can always calculate the distance between bottom. And differential parallax you can calculate using the difference between the stereoscopic parallax at the top and base of the object. So, here the differential parallax is equal to distance of bottom minus distance of top. So, this is the differential parallax of your image of that particular object. So, how do we use this stereoscopic parallax in height estimation? So, once you have all this information with you, you can always calculate what is the height of the object. So, here in this equation, h is basically object height which we want to calculate, h dash is flying height that is known, then differential parallax you can calculate using the previous method, and p is the average photo base length, right. So, this equation can be used to estimate the object height when you are having stereoscopic parallax, right. Thank you.